Hello everyone, this is Aidan for Fluid Mechanics 101, and in today's video I'm going to be talking to you about Green-Gauss cell and node-based gradient schemes. Now this is going to be a really interesting video. If you've ever wondered in your CFD code what the difference is in the gradient schemes between least squares, cell-based, node-based Gauss gradient schemes, but haven't really been able to find a good explanation, this is definitely the video for you. I'm going to be going through a worked example for how the Green-Gauss based gradient schemes work. You're going to see the difference between cell-based and node-based schemes, and I'm also going to look a bit at the skewness error which arises in one of the schemes. So by the end of the video you'll have a good idea about which scheme is actually more accurate and better to use for your simulations. So sit back, pay attention, take some notes. I know you're going to find this talk extremely useful. Let's get into it. So to start things off, what we want to do is think about variables in a CFD code and where they're stored. Now, in the simple diagram I've got for you here, I've got a reminder that all of the flow variables, so temperature, pressure, velocity, turbulent kinetic energy, are calculated and stored at the cell centroids. So that's the center of the cell there, which you can see in the diagram. And this is true for CFD codes OpenFOAM, Fluent and StarCCM. Slightly different for ANSYS CFX, which stores variables at the nodes. But for these CFD codes, all our variables will be stored at the cell centroids. Now, a reminder also that the CFD code will compute these variables at the cell centroids, but what we're interested in is the cell gradients. So we'd like to know what the gradient of these quantities are. So I'm going to use the grad or nabla symbol to denote the gradient. And what we'd like to know is what is the gradient of temperature, pressure and velocity at the cell centroid. And just a reminder for how we denote the gradient in vector formation. So in example 1, we can see that the gradient of temperature has 3 components in a Cartesian system. And they're the derivative of temperature in the x direction, the y direction, and the z direction. And we could choose any coordinate system we wanted, but it's common in CFD codes to use a Cartesian system with x, y, and z. So for a scalar field, temperature or pressure, or one of the components of velocity, the gradient has 3 components. And the way to think of the gradient is it's the rate of change of that variable in the x direction, the rate of change in the y direction, and the rate of change in the z direction. And what we'd like to know is how do we get the gradient at the cell centroid given the value of the actual flow variables, so temperature, pressure, velocity, which are calculated and stored at the cell centroids. So why do we need the gradient in a CFD code, and what is it used for? Well, just to give you some quick examples of what the gradient's used for numerically, the gradient is used for some discretization schemes in the convection term. So the main one being linear upwind differencing. We need the gradient of the flow variable in order to use a linear upwind differencing scheme. And if you want a reminder of how the linear upwind differencing scheme works, I'd advise you to go back and just have a quick look at the video that I've done on different discretization schemes, and you'll see there where the gradient comes in. We also need the gradient for the non-orthogonal correctors that we need. That's for any mesh that isn't perfect squares that are aligned with the flow direction. We need non-orthogonal correctors, and again I've also done a video on non-orthogonal correctors, so you can go back and have a look at that if you'd like a reminder. And finally, some source terms will also need the gradient in order to evaluate them. And just given for you there in the diagram a quick example of linear upwind differencing and why we might need the gradient. So if we know the value of the temperature at the cell centroid, that's Tp, then if we know the gradient at the cell centroid, that's grad or nabla T there, you can see that we can use the gradient to extrapolate and work out what the temperature is on the face of that cell. So really, one of the main reasons we need the gradient is so that we can extrapolate and work out what the face values are, because our CFD code computes and stores the variables at the centroids. And where does this gradient choice come in when you're running your CFD codes? Well, if you are an OpenFOAM user, you'll notice in the FV schemes file, you'll have to select the grad schemes entry there, and you can see that in this example there's a Gauss linear option chosen for the velocity gradient, and that's a cell-based Green-Gauss method. Or similarly, if you use ANSYS Fluent as your CFD code, then you have to select the gradient schemes in one of the drop-down menus for the spatial discretization. And you can see in the screenshot I've given for you there, a least squares cell-based gradient has been used. So there are different schemes that we can use to compute the gradient, and I've just been through a few examples of why and how you would need to use the gradient in the CFD code. But now what we're going to do for the rest of the talk is dive in and actually look at how does a Green-Gauss cell-based and a node-based gradient scheme actually work, and what calculations are going on behind the scenes that we might not see when we select these options. So the first thing that we're going to do is just have a little think about how we might compute a gradient in 1D in a general sort of example form, and then we're going to extend this to look at how is the gradient actually calculated for three-dimensional cells. So if we look at the example that we've got here on the screen, we've got three cells which are shown in blue, and what we've also got is we've got the temperature at the cell centroid. So we've got T sub P there, that's the temperature at the cell centroid in the middle, and then Tn, which is the temperature at the cell centroid on the right. And I should just point out here that I'm using temperature as the variable of interest. You could use any variable that your CFD code computes. You could use temperature, pressure, velocity, but I tend to use temperature because it's a nice, easy variable to understand, and we have a good conceptual grasp of what the temperature is. So if we know what the temperature is at the middle cell centroid and the right cell centroid, and of course in a CFD code the variation across and between cells is always linear, and we know the distance between P and N there, that's dPn, which is the distance, then we can take the difference in temperature and divide that by the distance, and that's going to give us the x component of the gradient on the face. So remember, of course, that our gradient is, we're going to have a gradient in all three directions, the x direction, the y direction, and the z direction, but because we're in 1D here, the gradient of temperature on that face there is 0 in the y and z directions, but takes a value of Tn minus Tp over the distance there in 1D. So that will give us the gradient on the face, but remember, of course, that the linear variation between cells will be different for the left cell and for the right cell. So I've got the left cell variation there in green and the right cell given there in red. And so we could do the same calculation on the left face of the cell to calculate the gradient on that face. And then what we would do to calculate the gradient at the centroid of our cell, that's gradient at Tp, we take the average of these two values. And this is one method that you could use to calculate the gradient in 1D. But we can see straight away that this method isn't very accurate and doesn't really extend to 3D. So what I'm going to do now that we've just had a think about what the gradient actually is and how we might go about calculating it, I'm going to show you how we can extend this to 3D and the methods that are actually used by CFD codes. And just to get you thinking about it, a reminder that in 3D our cells may not necessarily be squares or rectangles. We could have triangles, or we could have a general polyhedral cell with n sides. So the picture I've got for you here is an image of a pentagon. That's a 5-sided cell, and you can see that that pentagon there has 5 neighbors which aren't really aligned with any of the axes, and we'd like to calculate the gradient at the centroid of this cell here. And just as a quick summary of the different methods that we have available, there are 3 main methods of computing the gradient at the cell centroid. We have Green-Gauss cell-based, which in OpenFOAM is called the linear scheme. We have a Green-Gauss node-based scheme, which is called the point linear in OpenFOAM. And we have the least squares scheme. And just a quick point here that I'm not going to be looking at the least squares scheme in this video. I'm going to do a separate video on the least squares method because it doesn't use the Green-Gauss method, which we'll see in this talk. So we're going to focus on methods 1 and 2 for computing the gradient. And the main aspect of these Green-Gauss based schemes is we use the divergence theorem, or Gauss's divergence theorem, and we're going to use this to derive an approach that we can use to compute the gradient. So what we need to do is start with the general divergence theorem, which I've got for you there in equation 4. And for a general vector field B, then what we have is the volume integral of the divergence of the vector field B on the left-hand side is equal to the surface integral of the vector field B dot product with the normal vector on the surface of whatever volume we have there. Now, at first glance, the divergence theorem might look a bit arbitrary, and we might think, well, what does this physically mean? Where does it come from? And we might spend a long time looking up on the internet to try and work out what the divergence theorem actually is. But an easy way to think about what it means physically is if we have a box or a volume, as you can see there in the image, and we have some substance B inside it, which I've used these blue circular balls in there to denote this substance B, then in that box we may have an accumulation of balls or substance inside the box. And the term on the left-hand side of the divergence theorem means the accumulation of that substance within the box. And if there is substance accumulating in the box, then there must also be a flux of that substance across the surfaces of the box. And that's all that the divergence theorem is saying physically, is that the net flux out of the volume must be equal to the rate of increase inside the volume. So the substance B is conserved. You can think of it like a conservation law. So now what we're going to do is take the divergence theorem for the general vector field B and do a bit of manipulation so that we can put it in a useful form that we can use to calculate the gradient. Notice and remember that the gradient is given by nabla B, but it's not nabla dot B. It's a different operator. We want the gradient and not the divergence, so we have to do some manipulation to do that. And the trick to this manipulation is to take this general vector field B and write that as the product of a general scalar field T, in this case the temperature, and C, which is going to be another vector field. So you could always express a vector field as the product of some scalar field and another vector field. And if we substitute B equals to TC into the divergence theorem, that gives us equation 7. And now what we're going to use the product rule to split out the field T and the field C. And if we carefully use the product rule, we arrive at equation 8 there, which might appear long and a bit more complicated than what we had at the start. But the trick and the thing we're going to do to simplify is to take that general vector field C and set it equal to 1. So all three components of that arbitrary vector field C are going to be set equal to 1, and this allows us to cancel out a few of the terms in that product rule there. And what we arrive at when C is equal to 1, we arrive at equation 11 there. And equation 11 is a manipulated form of the divergence theorem, which you may see quoted but not often derived. And what you can see there on the left-hand side is we've got the gradient of the temperature field there. So we've got grad T, that's what we're looking for, integrated over the volume, and then we've got an expression there on the right-hand side for the flux over the surface. This is great, we're making good progress. Now what we need to think about is that divergence theorem is expressed for a general volume or a general 3D region of space. That could be any shape we want, but in our CFD code we know we've got cells which have a finite number of faces. So we could have tetrahedra, hexahedral cells, or even polyhedral cells, but whatever the volume is, we know it's got a finite number of faces n. And so what we can do is we can take that manipulated divergence theorem expression that we had, and we can look at the right hand side, which is a surface integral. And what we can do is replace that surface integral by the summation of the surface integral over each of the faces. And the way to think about this is by having a look at that diagram there for the pentagon. Now the pentagon will have 5 sides, n equals 5, and what we're doing is, instead of taking the surface integral over the entire surface, we're saying, well, the surface integral is actually equal to the summation of the surface integral over each of those faces. So the red face, the green face, the blue face, the yellow face, and the pink face, we'll take an integral over those faces and then add them up. And that will be equal to the volume integral of the temperature gradient inside the cell. So again, we're making further progress here, and this is looking really good. The next thing to do is remember that in the second order finite volume method, the variation of quantities across those faces will be linear. And so what that means is, if you take a look at that small simplified diagram that I've got for you on the right, is that at the ends of the faces will have a value of temperature, and the variation between them will be linear. And so what we can do now is play a very clever trick, and the trick is the integral across that face, because the variation is linear, is actually going to be equal to the value at the center of the face multiplied by the area. And you can actually do this derivation mathematically if you want, but I find it's a lot easier to convince yourself just by looking at the image there that the area under the curve will be the same if we take the value at the face center, TF. So this is fantastic. What this allows us to do is to take that surface integral on the right hand side of the equation there and replace that by the product of the temperature at the face, the unit normal vector at the face center, and the area of the face. And I've used the subscript f there in the equation, so it's really clear that what we're doing is we're just taking that value at the face center f and just multiplying them. So what have we done now? In that boxed equation, what we've got is we've got an expression for the volume integral of the temperature gradient, and that's going to be equal to the sum of the temperature, the unit normal vector, and the area at the center of each of those faces. So what we could do to work this out if we wanted is just go to the center of each of those 5 faces, get the temperature, the normal vector, and the area, multiply them, and then add them together. And this is fantastic. This is looking really good for us so far, but we're not quite finished yet because we want the temperature gradient. We don't want the volume integral of the temperature gradient. So the next thing to remember is, in the second order finite volume method, not only is the variation across the face linear, but the variation across the entire volume of the cell is also linear. So the way I tend to think of this is given for you there in the diagram, and you can see that the quantity T, temperature, varies linearly across that entire cell. And what that means is we can use the same clever trick that we use for the face integral, and we can say, well, rather than integrating the temperature across the entire volume, we can just take the temperature, or the temperature gradient in this case, at the cell center and just multiply that by the volume. So again, this allows us to get rid of the integral if we take the value at the center or the centroid of that volume. And so what that allows us to do is to replace that volume integral by the multiplication of the temperature gradient at the cell centroid and the volume, and that gives us equation 12, which we can see there. And we've almost got the temperature gradient at the cell centroid. The last thing to do, of course, is to just divide both sides by the volume of the cell, and that gives us an expression for the temperature gradient at the cell centroid. Fantastic, this is what we were looking for. And just a reminder that we could use this same approach for any quantity we wanted. I've used temperature because I find it easier to follow, but you can use that for velocity, turbulent kinetic energy, pressure, etc. The form for the gradient will be the same, and what it is going to be 1 divided by the volume of the cell multiplied by the summation of the face value of that quantity multiplied by the normal vector and the area of the face. And just looking at those expressions there, what we can see is that the left-hand side is, of course, a vector quantity. It has 3 components in the x, y, and z direction, and the right-hand side is also going to be a vector quantity. And the reason we get a vector quantity is because we're multiplying by the normal vector at the center of the faces NF, which will have components in the x, y, and z direction. So what I've just got for you there at the bottom of the slide is a summary of the process and how you would do this numerically in a CFD code to calculate the gradient. The first thing you would do is get the value at the face center of the quantity you wanted. It could be turbulent kinetic energy, temperature, whatever quantity you were looking at. You would take that quantity, multiply it by the normal vector and the area. That will give you your vector quantity, and then sum up over all of the faces on the cell, and then divide that by the volume of the cell, and you've got the gradient at the cell centroid. So this is the Green-Gauss method overall for computing the gradient, but we're not finished there. We still need to look at cell-based and node-based approaches, and these are slightly different. And the way they come in is the way that we compute the value at the center of the face. So that's TF or KF. That's where the difference will come in between these schemes. But before I do that, I'm just going to do a quick example to run you through. If you've been a bit overwhelmed by the maths, this is an easy example which you can use to just check that you understand what's going on. What I've got for you here is a simple square cell where each of the faces has an area of 1 meter squared, and we've got normal vectors pointing out of the cell. And at the face center of each of these cells, we've got a temperature of 150 on the left, 175 on the bottom, 200 on the right, and 225 on the top. And what we'll do to work out the temperature gradient at the centroid of this cell is to take each of those faces in turn and take the temperature, multiply it by the normal vector and the area, and then add them up. And if you follow equation 15, you can get that expression and then add them up and divide by the volume, which in this case is 1 because it's a square, and we get the gradient is 50, 50, and 0, 3 components. And actually this is what we expect. We can just sort of look at the cell by inspection and see that in the x direction, left to right, the gradient's going to be 50 degrees per meter because it's a 1 meter long cell. And in the y direction going up, the gradient is also going to be 50 per meter because the change in temperature is 50 and the distance is 1. And in the z direction, the gradient is 0. So that should be a quick example which you can just run through yourself with pen and paper if you want, just to check that you understand how the Green-Gauss method is working. You can always do this for a more complicated cell if you want to. But now let's look at cell-based and node-based schemes. So the difference between the two methods, just to reiterate, is the method that we use to calculate that value at the face center, which I've highlighted in red there in equation 17. So if we calculate TF using linear interpolation, we're using the Green-Gauss cell-based method, or if we calculate by nodal averaging, then we're doing a Green-Gauss node-based method. And don't worry if you don't follow that so far. I'm going to go into detail in each of those methods in the next few slides. So starting with the cell-based method, you may have seen this linear interpolation scheme before. It's quite common and it's the scheme that's used for central differencing. And the way we would do it is the value on the face there, TF, is going to be a linear interpolation between the centroid values, TP, and Tn of the cells that surround that face. And this fraction f there is just going to give the fraction of the distance between those two centroids. So if the face is very close to one of the cells, then of course linear interpolation is going to be biased towards whichever cell the face is closer to. That's standard linear interpolation, and you can give it a go for yourself if you want. And that is the cell-based scheme. It's called a cell-based scheme because implicitly there we're using the values at the centroids of the two cells that border that face. That's why it's called a cell-based scheme. The alternative is to use a node-based scheme, and the way we would do that with the nodes is we would add up the temperatures on all of the nodes that surround the face, So if you look in the diagram there, you can see the nodes are highlighted in green, and what we would do is take the average of all of the nodes that surround that face, and by taking the average, that would allow us to compute the temperature at the center of the face. And of course that's a node-based method because we're using the surrounding nodes. Now, what's the difference between the two schemes? Which is better and which one should you use? Well, if you think very carefully about the methods, what you'll find is that the cell-based method leads to a skewness error. Now, the skewness error is different to a cell skewness that you might see in your meshing application. The skewness error is something very specific, and it comes in when we think about the alignment of the cells. So what I want you to do first is just have a quick think about the two cells which I've shown you there on the screen. We've got a triangle on the left and a quadrilateral on the right, and the blue dots show the centroids of the two cells. Now, if we draw a line between the two centroids, we have a vector dpn there, and what you can see is that when the cell is skewed or not aligned, that vector d doesn't pass through the center of the face. And so what that means is when we use linear interpolation between the two cell centroids, so P and N, when we linearly interpolate between them, what we're doing implicitly is calculating the value where that vector intersects the face, so the red dot there. That's where we're computing the temperature. However, if you remember back, we want the temperature at the center of the face. The reason we want the center of the face is because we use that clever trick where the variation across the cell is linear, and so we take the value at the center of the face. And so there's a small error here between the face center and the intersection with the vector d, and this error is called the skewness error, and it may result in a slightly different calculation of the temperature at the center of the face. Now, the node-based approach doesn't have this skewness error, so implicitly the node-based approach is more accurate than the cell-based approach. However, the node-based approach is slightly more difficult to do because we have to calculate the temperatures on those nodes as a separate calculation, and I haven't gone into detail here about how that's done. Just appreciate that the node-based approach is more expensive to do. And as another side point here, we should remember, and this will be shown in a later video, that the least squares method also doesn't have a skewness error. So as a summary, remember that the Green-Gauss cell-based approach does have a skewness error if the cells aren't aligned well, or if your mesh has low quality, as you might expect. So the cell-based approach isn't preferred when you're choosing your gradient scheme, and a node-based or a least squares approach will get you a more accurate answer. So just a quick summary of what we talked about today. Remember that it all starts with Gauss's divergence theorem, and by manipulating Gauss's divergence theorem, we come up for an expression for the gradient at the centroid of the cell, and this gradient at the centroid of the cell is expressed in terms of values at the center of the faces of those cells. And then we have two different methods for computing those values at the center of the faces. We have a cell-based approach with linear interpolation, and we have a node-based approach which uses averaging. And the cell-based approach can lead to a skewness error if the mesh is of low quality. And so for that reason, it's recommended in the Fluent manual and by many CFD codes that if the mesh is bad, you should go for a least squares or a node-based approach, as this will not have a large skewness error. However, it's worth noting that the node-based approach is more expensive. So that just about wraps up the talk. I hope you found the talk extremely useful. The next video I'm going to be doing is on the least squares gradient scheme, and that, as you'll see, that's going to be slightly different to the Green-Gauss schemes that we've looked at here. So keep watching this space. That video will be out soon, and I know you'll find it as interesting as this talk. In the meantime, if you like the video, just leave a thumbs up or drop a comment down in the comment section below and let me know, was there anything that you didn't understand, or did you spot any mistakes in the work? I always like hearing your comments from you, and try to get to those as quickly as I can. And for those of you who want more, you can always go and check out my website or go over to Patreon, where you can find some additional extras for things that I haven't got here. You can pick up a copy of my CFD Fundamentals course, and I've also got a template on there for the lecture slides that I use in these courses. So if you ever wonder about how I make them, how I make the graphs and the images and the text, you can head on over to Patreon and you can pick up a copy of that. So until next time, I look forward to hearing from you, and thanks for the support.